Welcome all of you. Myself Dr. Genudas, Associate Professor in the Department of Physics, रयत शिक्षण संस्था SSGM College, Kopergaon. Now on second chapter, work and energy, this is my next lecture, and in this lecture we going to derive the formula for work done by varying a force, or this is also known as a spring force, means work done by spring force. Now in last lecture we have seen we have derived the formula for work done when force is constant, and this is W, total work done, W, which is equal to dot product of force into displacement. Now here our aim is to calculate work done by varying a force, and for this situation consider the figure. So this is the figure to find the work done by varying a force or spring force. Here we have considered, in figure A we have considered a spring having a spring constant K, and one end of the spring is fixed to a vertical support such as a wall, and other end is tied to block placed on the smooth horizontal surface. So this is situated, this is as shown in figure A. Now here let x equal to 0 be the position of block when spring is in natural length, that is in figure first we have shown this. So here this is the situation where we have shown this. So see, this is the figure. So this is the position where x equal to 0 be the position which we have considered when spring is in natural position or natural length. Means here spring is not stretched or not compressed, it is its natural position. So as K is the spring constant, then force on the block by spring is equal to K times the elongation of the spring. So if we assume the spring length is x and spring constant is K, so force exerted on the block is given by F, which is equal to K into x, or product of spring constant multiplied by elongation of the spring. Now let us calculate the work done by the spring when block moves from position x equal to 0 to x equal to A. Means we have to calculate the work done when this body is displaced from this position to this position, means x equal to 0 to x equal to 1. And for this we consider intermediate stage, that is suppose that block moves from position A to position A dash, means our aim is to find the work done from x equal to 0 to x equal to A, and for this we consider that block is moves from A to, so this is the situation, block is moved from this A to A dash, small displacement. Means we have considered that block moves from point A to A dash such that distance A dash is equal to dx. So as this is a small displacement, so this is denoted by dx. The force varies from position A to A dash, means when block moves from A to A dash, so which is shown by a red circle. So as displacement is small, so force may be taken as a constant. It varies, but due to the small displacement we consider that variation in the force is also very small, and so we take it as a constant. Let F be the force, then work done by the force F when block moves from A to A dash, which is shown by these two circles, A to A dash. So small work done will be dW, and as per our previous knowledge, this small work done will be dot product of force into displacement. As force and displacement are oppositely directed, so this equation which we have considered here, we may write this. So this is the derivation, that is f dot ds. So this is the derivation. Small work done will be dw, which is equal to minus k into kx into dx. So here ds or dx, you may take any symbol for this. So why we have taken negative sign? Because force and displacement are oppositely directed. Now as force is equal to k into x, the work done in moving a block from position x to x0 to x equal to x1, that is from point A to B, can be calculated by integrating this equation. Which equation? dw. So this is the equation we integrate dw, which is equal to minus kx ds, or also this is also dw, which is equal to kx dx. So you may write any one. So we integrate this, and so this is the integration. So integration will be w, which is equal to minus sign as it is. So integral is 0 to x1, because we are finding the work done when body moves from A to B, that is from distance 0 to x1, kx dx. So here k is constant. So integration of this we find integration will be x square divided by 2 x dx. इंटिग्रेशन काय असेल? x square divided by 2 upper limit and lower limit. So upper limit is x1, lower limit is 0. So total work done w will be minus 1 upon k x1 square upper limit, minus minus become plus lower limit, and as value of x is equal to 0, so this is equal to 0, and so we get expression for the work done w, which is equal to minus 1/2 k x1 square when body moves from position A to B as shown in figure B. Similarly, if block moves from x1 to x equal to x1 equal to x, means again this is a case when we move from x equal to 0 to x equal to 1. Now if block moves from x equal to 1 to x equal to 2, means again in similar manner, then work done will be w, which is equal to body moves from x1 to x2, which is equal to integral in the limit x1 to x2 minus sin kx dx. So here this work done will be, again k is constant, integration of x will be x square divided by 2, so upper limit minus lower limit. So upper limit is minus 1/2 kx2 square, minus minus become plus, so this will be 1/2 kx1 square. So we write the positive term first, and work done when body displaced from x1 to x2 will be 1/2 kx1 square minus 1/2 kx2 square. Now if the block brought to position x equal to x1, that is, it means that block moves from position x equal to 2 to x equal to 1, means again block comes to its original position, then work done will be find out in similar way, only we change body moves from x2 to x1. So this will be again integrate with this, putting upper limit minus lower limit, we get 1/2 kx2 square minus 1/2 kx1 square. Now if we add these two equations, this is first and this is second, that is when body moves from x1 to x2 and when again body moves from x2 to x1. So if we add these two equations, adding these two equations, that is work done by displacing body from x1 to x2 plus work done when body moves from x2 to x1, which is equal to 0. So what is the conclusion for this? So conclusion is total work done by a spring force during the displacement of block from position x1 to x2 and brought again to its original position, means x2 to x1, is equal to 0. that is net work done by spring force in a round trip is 0. Now here we using this formula we study the different cases. So this is first case, various case. First case is when spring is initially in a natural length, that is x1 equal to 0 and stretched to position x2 which is equal to x, then work done is given by the formula W which is equal to minus sign 0 to x. So here we take the limit where from which position to which position body displaced. So here initial position is x equal to 0 and final position x2 equal to x. So 0 to x minus kx dx. So this will be minus 1 half kx square. Now second case is if the reverse case, that is if spring is initially stretched at x equal to 1 and released to its natural position, means x2 which is equal to 0, means initially its position is x1 which is equal to x, so stretched position, and final position is its natural position, that is x equal to 0. Then work done will be, this is second case, work done will be W. So this is the second case, W will be minus k. So initial case is x and final case is 0. So limit is x to 0, kx dx. So this will be again minus minus sign become plus. So 1 half kx square, upper limit minus lower limit. Now third case is if spring is initially in a natural position, that is x1 equal to 0 and compressed to distance x. So x2 will be minus sign, then work done will be W which is equal to 0 to minus x, because this is a compressed case, not elongation. So integral limit is 0 to minus x. This is third case. So this will be minus kx dx. So k is constant. Integral of x dx will be x square divided by 2. So total work done will be 1 half kx square minus psi. Now fourth case is if the reverse case, if the spring is initially in compressed position, means x1 equal to minus x and released to its natural position, so x2 will be 0. Then work done will be using same equation, same concept. So W will be minus sign. So initial position is minus x and final position is 0. So integral limit is minus x to 0 kx dx. So again here minus sign is there. So upper limit will be 0 and lower limit minus minus become plus. So work done will be 1 half kx square. Now last case is, this is if the spring is initially in the compressed position, means x1 equal to minus x and it is stretched in position x2 which is equal to x. So work done will be using same manner, W which is equal to minus, integral limit will be minus x to plus x. So kx dx which is equal to 0, because when we find the integral, k is constant, x square divided by 2. So upper limit minus lower limit. So upper limit and lower limit. So this integral gets cancelled. Now we see the different cases. Now we will start with next article, that is conservative and non-conservative forces. We always come such type of forces. A force is said to be conservative if work done by the force in moving a body from one point to another point depends only on the position of these points and not on the path, then work done, then this force is called as a conservative force. So for this, consider the figure which is here. So this is the figure to understand this conservative force. So this is the case, that is here we have take two positions, say A to B, particle moves from position A to B and there are two paths. that is path first and path second. Now the work done along path first, that is when it goes from position A to B along path 1. So this work will be W1. So integral will be A to B, position A to position B. So F dot dr, and along path second, that is dW. So this path is shown in figure. So path second is A to B. Particle goes from A to B but along path second. So work done will be F dot dr. Now if W1 is equal to W2, means work done by the force to move the body from position A to B along path first and along path second are equal, then this force is said to be conservative. If the force done in moving a body from point A to B along path 1 is W1 and that from path B to A is W2, so we find the separate work done. So W1 will be integral limit 0 to A F dot dr, and along path second, that is this will be the W2 dash, which is equal to limit B to A. So this will be F dot dr. The total work done around a trip of journey along a closed path from point A to B and path 1 and then from B to A along path second is, so total work will be W, which is equal to W1 plus W2 dash, which is equation number 1. Now the work done in moving a particle from A to B along path second is W, which is equal to integral limit A to B F dot dr, but this is opposite to the W2 dash. So we write W2 dash, which is equal to W1. Hence equation number 1 becomes, we substitute this value in equation number 1. So W will be W1 minus W2, which is equal to 0 for conservative force. Means for conservative force, total work done will be 0. So we will stop here and we continue in the next lecture. So we will stop here.